Hello everyone, and welcome to my channel. This is a channel for educational purposes, and we take our time to look at different theories of everything, do deep dives into these theories so you can see how they can affect your life in positive ways through knowing about them, but you don't know about them because they've been suppressed, and unless you've spent your time digging on the margins a lot, these probably escaped your notice. And so today is our 427th video that we've done on the reciprocal system of theory from Dewey B. Larson. Mr. Larson proposed his two fundamental postulates, stating how he felt the universe operated back in 1959, and he called it the reciprocal system of theory. He also called it the universe of motion. And then he went through a process of deduction where he said, if this is true, then that's true. If this is true, then that is true. And he compiled his theoretical universe about how the universe would operate if his two fundamental postulates were correct. And then in many of his books, he compares his theoretical universe with the measured universe of the legacy scientists, what they had put together in their laboratories and compiled in their tables after decades or centuries or millennia of accumulating different results. And Larson, being one guy with no budget and no resources, was able to more or less duplicate many of their findings. So we'll look into some of those having to do with chemistry today in his book, Basic Properties of Matter. We're looking at chapter 3. It's called Distances and Compounds. It looks at the interatomic distance. And for Larson, those are the distances between atoms in closest packing in the solid state. Now, the legacy scientists believe it is the actual size of the atoms. Larson believes it's the actual distance between them. Now, most of Larson's theory is put forward in his first postulate of the two. The second postulate basically just has to do with math and geometry, but the first postulate articulates his universe of motion, and he says that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so there's really 4 things we need to look at here. What is motion? And then we look at the reciprocal relation between space and time, and we look at the 3-dimensionality of space and time, and and also motion, and the discrete nature of space, time, and motion. Okay, so for Larson, motion is not exactly what you think. Normally we think of vectorial motion, a motion in a direction. But Larson is referring to what you call a scalar motion. This is a motion that has a magnitude, but it has no specific direction. You can envision this using a balloon that you put dots on with a magic marker. You blow up the balloon, all of the dots will be moving away from each other. And if you contract the balloon, all of the dots will be moving toward each other. They won't be moving in any specific direction. Rather, they will be moving really in all directions. every location on the surface of that balloon will be moving relative to every other, or really will be moving, period. Every every point on that balloon will have a motion, and it will be moving in all directions. Now, one thing that's pretty important to note is if you look at, say, you look at motion, normal motion, I guess vectorial motion, or a motion like this, a scalar motion, it takes 3 dimensions of space to represent 1 dimension of motion. So when we're talking about this kind of example with this expanding balloon, we're only talking about 1 dimension of scalar motion. So that's something that I don't emphasize usually, but it's important to, I should emphasize it more. We'll get into some of the ramifications later. Okay, now, so we've got this scalar motion that doesn't have a direction, or it's really only directions are in or out. And this is kind of like a more flexible kind of motion. And it is not really well known by science. They've acknowledged its existence, but not its importance. So Larson is really the first person, and in particular the first person to come up with a universe made out of motion, which many other people have done before in the past, but he's the first person to make it work, partially because he identifies it as scalar motion. Another reason that Larson is able to make it work is because he denotes motion as the relationship between space and time. So he's defining motion as the relationship between space and time. You can see that most clearly in the concept of speed. Speed being certainly a kind of motion, and speed having a relationship, in particular a reciprocal relationship between space and time. You can express speed, for example, the bicycle is moving 10 miles per hour. 10 miles of space in 1 hour of time. Space over time. Now, if you decide to double the speed, you can say that, well, now the bicycle is moving 20 miles per hour. 20 miles of space in 1 hour of time. But alternatively and equivalently, you can say the bicycle is now moving 10 miles per half hour. So you can either multiply the space or divide the time. That's a reciprocal relationship. So it does fit the example of speed. But Larson extends that and says that this relationship between space and time occurs in all forms of motion, and that really all of our scientific entities or quantities are forms of motion, where space and time are reciprocally related. So he says that energy is a kind of motion, matter is a kind of motion, force is a kind of motion, power is a kind of motion. And they all have space-time, space in the numerator, or time, and time in the denominator, or space. So one or the other is in the numerator and the other is in the denominator. And they can come in 1, 2, or 3, at least, powers. And they can actually come in up to 6 if it, in the proper circumstances. For example, matter in Larson's reckoning is time to the 3rd power over space to the 3rd power. It's really like three-dimensional energy. Energy is time over space. Matter is time to the third power over space to the third power. And in fact, you can see the relationship between energy and matter there. The relationship is space to the second power over time to the second power. That is the square of speed, the speed of light. The E equals mc squared is easily derivable, or is you can see how the units work out if you plug in E equals mc squared to that. But the example that I was using is density. So density is matter per volume. So in the reciprocal system, density would be time to the third power over space to the third power over space to the third power, because volume is space to the third power. So density would be time to the third power over space to the sixth power. Just an example how it can get up over 3. Also, space and time come only in discrete units. You have to have a full unit of space before you have space. You have to have a full unit of time before you have time. Now here with the discrete unit postulate, in Larson's universe of motion, first of all, you have to be able to accept the fact that motion exists before something moving exists. You have to be able to accept motion preceding the thing that's moving. You can have an empty universe with nothing in it, and you would still have motion. It's ubiquitous and eternal. This outward motion that Larson calls the progression, outward motion of that balloon in 3 dimensions. And then you also need to be able to accept the contents of the universe being space and time, as opposed to the container. For thousands of years, we've thought of the universe as a space-time container through which all of our actions occur. Our actions occur in space and through time. But in Larson's universe, space and time are the very contents of the universe. So these are kind of 2 mental hacks that you have to make before you can really accept the reciprocal system. Now with the discrete unit postulate, if you have exactly 1 unit of space, which is the minimum, over 1 unit of time, which is the minimum, then you have what Larson calls unit speed, space over time being speed. And unit speed is the speed of light. This is the background speed of the universe, outward in all directions at the speed of light in 3 dimensions. And Larson calls this the progression of the natural reference system. So this is always there. And this is what the universe is built out of. The universe is built out of really reversing that progression and harnessing it, more or less. And so that's kind of where you get into these, chemistry investigations. Now, the other part of the discrete unit postulate, so you have this boundary, space over time, 1 unit of space over 1 unit of time, the speed of light outward in all directions. That's the ether. That's the origin. That's the 0 point in Larson's universe. He takes his measurements from that reference point. And then that basically means that half of the universe is actually moving faster than the speed of light, which is blasphemy to the legacy scientists. Larson calls that the cosmic sector. And then half the universe is moving slower than the speed of light. That's the material sector that we're familiar with. And in that material sector, we observe 3 dimensions of space, like Euclidean geometry or XYZ coordinates of volume in a still frame, 3 dimensions of space in a still frame, and progressing time or scalar time. Time is always getting later and later and later, or farther and farther and farther apart, but in no specific direction. It's just, either it's going outward, it's flowing, the progression of time. Now, if we cross that unit speed boundary into the material sector, we would observe 3 dimensions of time in a still frame, and we would observe clock space. Space is always progressing, flowing, going further and further out, further and further apart. So that shows that when you cross that boundary, you have to reverse the roles of space and time. The same is true within each sector, within the unit boundary. Okay, so within the material sector, you have a sub-region where you observe interactions between two particles, 2 atoms, 2 molecules, that they interact in less than 1 unit of space. But you only can have 1 unit of, you have a minimum of 1 unit of space. So if you don't have a unit of space, then you don't have space. So if you don't have space, then it has to be time, because the universe is composed of time and space only. So it's one or the other or both, and if it's not space, it has to be time. Larson calls this region the time region. And in the time region, this is where you have atomic and molecular interactions. And when you cross the boundary into this time region, the unit space boundary, which is 4.56 times 10 to the minus 8 meters, then you change the rules again. The rules reverse, and the progression is now inward, and gravitation, which is the reverse of the progression, that's the contracting balloon, is outward. So the progression and gravitation change their roles, and you have to account for that in the time region. And there is an analogous space region in the cosmic sector in less than 1 unit of time. Then you only have space, and the progression is moving inward, and gravitation is moving outward. Now, one thing to make clear is we only see time. We do not see space. And so when something occurs in time, we see it as its inverse in space. Larson calls that equivalent space. So within the time region, what goes on in the time region occurs in time, but we see it in its inverse manner in space. And that's what Larson calls equivalent space. Just to make it even more complicated. But just keep in mind, it's not that complicated compared to legacy science. It's incredibly simple compared to all the rules and rigmarole of the science that you learned in high school. This is elementary compared to that. But it is complicated, does have, certain rules that you have to understand. But compared to, science that you're learning in high school and college, it's very simple. Which, from Occam's razor, indicates that it's probably more correct. Now, the last thing that I will say is, so atoms are basically formed out of rotations. You start with 2 photons, which are simple harmonic motions or vibrations. But those vibrations of photons are moving outward with the progression. So they have to be slowed down in 3 dimensions before you can get them to gravitate and then eventually become atoms or matter. And these are notated by Larson as 3 separate rotations. Primary 2-dimensional rotation, a secondary 2-dimensional rotation, and another 1-dimensional rotation in the opposite direction. And so every element in Larson's system has a 3-number rotational combination. And Larson is able to identify the interatomic distance between different atoms as the area, the place where the progression, which is constant, is equal to gravitation, which is variable. So there's a place there, a place of equilibrium, and that is the place where there is an interatomic distance. Now, in this chapter here, Larson gets into figuring out the interatomic distance between molecules, between compounds, and so that gets into a lot of more complicated stuff. So you might not understand much of this, but we're just going to move through this to kind of get through Larson's thinking, and hopefully we can finish the chapter either today or tomorrow and then move on to the next thing. This chapter, I wouldn't have written it or put it here, but this is chapter 3. He spent chapter 2 going through the interatomic distance, and that was relatively straightforward. But then when he goes into this third chapter, he introduces a lot of other stuff that you need more background information. So here we go. The same kind of a deviation from the results of the apparent direct interaction between two individual atoms occurs on a larger scale where there is a group of atoms that is acting structurally as a radical. Okay, a group of atoms acting structurally. Also, he uses the term apparent, the apparent force interaction, because these force fields are only as if, according to Larson. It's like a scalar motion. An inward scalar motion, it looks like gravity. It looks like the force of gravity. If you take one of the dots on the balloon and you assume that it's motionless, you arbitrarily assign it to be motionless, then it looks like all of the other dots are moving toward that one dot, and that there is a force field, that's carrying all the other atoms toward it. But that's not the case. Every atom is moving toward every other atom. But by assigning the reference point to 1, you can make it look as if there is a force. That's why he calls it an as-if force. Okay, many of the properties of molecules composed in part or entirely of radicals or neutral groups are not determined directly by the characteristics of the atoms, but by the characteristics of the group. The NH4 radical, for example, has the same specific rotations when acting as a group as the rubidium atom, and it can be substituted in the NaCl type crystals of the rubidium halides without altering the volume. Consequently, the interatomic distances have no direct significance in compounds containing these groups. It is theoretically feasible to locate the effective centers of the various groups and to measure the intergroup distances that correspond to those calculated from theory. But this task has not yet been undertaken, and it will not be possible at this time to present a comparison between theoretical and experimental distances in compounds containing radicals comparable to the comparisons in tables 1 through 12. Some preliminary results have been made, however, on the relation between the theoretical distances and the density in complex compounds. There are a number of factors not yet investigated in detail that have some influence on the density of solid matter, and for that reason, the conclusions thus far derived from theory are somewhat tentative, and the correlation between theory and observation are only approximate. Nevertheless, certain aspects of these tentative results are significant and are of enough interest to justify giving them some attention. If we divide the molecular mass in terms of atomic weight units by the density, we arrive at the molecular volume in terms of the units entering into the density measurement. For present purposes, it will be convenient to convert this quantity to natural units of volume. The applicable conversion factor is the cube of the time region unit of distance divided by the mass unit atomic weight. In the CGS system of units, it has the numerical value of 14.906. Now, if you can derive that yourself, then you can really prove how well you understand the reciprocal system. I'll have to try it sometime, but I'm going to take his word for it for now as we move on. In Table 13, the average volumes per volumetric group of a representative number of inorganic compounds containing the radicals V as calculated by from the measured densities are compared with the cubes of the interatomic distances, which he calls SO3. I guess space sub-zero to the third power, as calculated on the theoretical basis previously described. So he's got molecular volume here, and the various values. These values are in angstroms, and which is 10 to the minus 9. I don't know if that's 10 to the minus 9 meters or centimeters, but he's got all the specific rotations here. The rotations of the atoms plus 1 is basically the specific rotation in most cases. And he'll calculate here 1.261. The observed value is 1.241 for sodium. I don't even know the name of this. NaNO3. And then KNO3, potassium. I guess that's, nitrous oxide or something. 1.608. Value observed 1.565. And then he's got this calcium. Nitrous oxide, dinitrous oxide, 1.554, observed 1.565. So anyway, he's getting close to the values, but they're diverging quite a bit more than they have in past tables. The specific electric, there's another, 30 or 40 compounds here. So, you can refer to those yourself if you want. The specific electric rotation, C, for the compounds with the normal orientation is 4. As in the valence 1 binary compounds, those with the magnetic orientation take the neutral value 5. The applicable specific magnetic rotations for the positive component and the negative radical are shown in the columns headed AB1 and AB2, respectively. Columns 2, 3, and 4 give the molecular mass, the density of the solid compound, and the number of volumetric units in the molecule. So in Larson's system here, the volume is quantized, just like the everything else. Everything is quantized, the discrete unit postulate. Here again, as in the earlier tables, the calculated and empirical values are not exactly comparable, as the measured values of the densities have been used directly rather than being projected back to zero temperature, a refinement that would be required for accuracy, but is not justified at this early stage of the investigation. In this table, again, Larson is one person and he doesn't have infinite resources, so he has to make decisions about, what he's going to calculate. In this table, there are 5 pairs of compounds, such as calcium dinitrous oxide and potassium nitrous oxide, or whatever that is, NO3, in which the intergroup distances are the same, and the only difference between the pairs, so far as the volumetric factors are concerned, is in the number of structural groups. Because of the uncertainties involved in the measured densities, it is difficult to reach from conclusion on the basis of each pair considered individually. But the average volume per group calculated from the density in the 5-2 group structures is 1.267, whereas in the 5-3 group structures, the average is 1.261. It is evident from this that the volumetric equality of the group and the independent atom, which we noted in the case of the NH4 radical, is a general proposition, in this class of compounds at least. This is a point that will have special significance when we take up the consideration of the liquid-volume relations. In closing the discussion in this chapter, it is appropriate to reiterate that the values of the interatomic and intergroup distances derived from theory apply to the separations as they would exist if the equilibrium were reached at 0 temperature and 0 pressure. In the next 2 chapters, we will consider how these distances are modified when the solid structure is subjected to finite pressures and temperatures. Okay, that is the end of chapter 3 on distances and compounds, and chapter 4 is on compressibility. So he's going to look at pressure and how it affects, volume. How much does something shrink if you put a lot of pressure on it? If you, squeeze it down, some elements and compounds will shrink a lot. Think of like a cotton ball or something, or a brick wall. If you squeeze that, it doesn't contract very much. So that's what he's going to be getting into here in this next chapter. I would just say, keep hanging in there. This is incredibly difficult stuff, but it's incredibly worthwhile if you can kind of get the whole picture. And Larson is doing his best to articulate something that's never been articulated before. So cut him slack, and hopefully, that will be part of my role moving forward, is to take what Larson wrote and translate it for lay audiences so that they can understand it. Because when Larson writes, he's not really writing for other people to comprehend it. And some of Larson's followers, the way they write, same thing. They're just trying to get their ideas out there, and they're not necessarily going to be understood until they're simplified. But we have to trudge through it to get to that point. So thanks for tuning in today.